So let's just begin with a song. You may have heard the song. Let's just read the first 4 lines. It's called Little Things. The little drops of water, little grains of sand, make the mighty ocean and the pleasant land. Then goes on. But that's an interesting thought. The ocean is actually just lots of drops of water. But the ocean is much more than drops of water. So you can see what that is. Next slide, please. And here is a story. So this is a Buddhist text from the 1st century BC. It's called Milinda Panna. Milinda's Questions. That's the title of the book, of the text. So here's the story. So I'll just tell you the gist of the story. So there is a king called Milinda. He goes to this Buddhist monk, Nagasena, and he asks, "Sir, what is your name?" Then the monk replies, "My name is Nagasena, but that's only a designation in common use. There is no permanent individual by that name." Then the king is astonished. He says, "That is meaningless. You're saying there is no meaning to you. There is no Nagasena. Somebody could kill you and there will be no murder because there is no Nagasena." Then he asks, but then the king goes on saying, "So what is Nagasena? You're saying it is just a designation. Is it your hair? No. Is it your nails? No. Is it your teeth? No." Then finally the monk replies, maybe like the next slide. The monk says, "Dear king, you're a very wealthy person. You're a king. You came in a chariot." I'm sure you're all familiar with chariots. Hopefully you don't ride one still. So the king asks, the monk asks the king, "You came in a chariot. Please tell me, what is your chariot? Is your chariot the wheel?" He says, "No." "Is your chariot the spokes?" "It's not." "Is your chariot the yoke?" "It is not." "Is your chariot the other parts of the?" He names each part of the chariot and asks, "Is this a chariot?" And the king says, "No." "And what is your chariot? Is there a chariot or is there not a chariot? Does a chariot exist?" So the king replies, "Sir, I understand your point. It has all these parts, and that is why it comes under the term chariot. That's what it means by chariot." And the monk replies, "Yes, you have understood the meaning correctly. Just because there are so many parts that are together in a certain fashion, we call it a chariot." So this is, of course, it's a philosophical story from a long time ago, but it's something we should all think about. Maybe let's go to another slide. So in our day-to-day interactions, we think about so many things. I think of a podium, I think of a mic. Everything is composed of so many parts. But when I push a podium, I don't need to worry about all the molecules that are sitting here, that are bonded to something else, that are stuck with glue. I think of this as a podium, and that is a meaningful statement. I can use this to stand, to hold, to rest. So we come up with so many constructs like this. We talk about society. What is society? Society is just people, so many people. Is it even meaningful to talk about society? How can you say something like a certain section of society has these characteristics? This society will respond in that way. We do make these statements day-to-day basis. We all do. But the society is just many human beings. So how does this acquire meaning? When is it meaningful? And so on. So you can talk about human beings, but human beings is just a collection of organs. Organs are just a collection of tissues. Tissues are just a collection of cells. Cells are just molecules. Molecules are atoms. Subatomic particles, quarks, maybe strings, or some other big question mark. So everything here is actually composed of many things below. Everything is what we call an effective construct. It is meaningful to talk about molecules, because we know molecules exist, we know we can do things with them, and we can work with molecules while forgetting the fact that they're made of atoms. We don't need to worry about it. We know a molecule exists, we can operate it. So we have this notion of effective construct, and this is true in all fields, not just in science, not just in physics, in every area of life we have these effective constructs. Why is it meaningful to have this? It doesn't have to be this way. Nature doesn't have to be this way, that we have fixed objects that have meaning, in spite of having many parts. So in science is a very important question. We'll see how we can understand this. So we can think of things like a ball, a tree, a man, the earth, the sun, anything else. Everything else is an effective construct. It's actually composed of many parts, but if you give it a meaning, it behaves like one coherent entity, whereas it's made of so many parts. In reality, it's made of so many parts. This is an especially important question for science, physics in particular, because we try to describe nature. We write a law for a ball that is bouncing. We write laws for the sun that is rising, eclipses. But if the sun itself is made of so many parts, is it even meaningful to write an equation for the movement of the sun, the motion of the sun? So all science is in terms of effective constructs. So we have to think about at some point we should worry about how we can justify this. What is it that we're actually writing about, and how were we allowed to do this? How come we're still able to make meaningful statements? So let's see. Okay. So at least for physical laws, there are two important constructs here. There are two important notions associated with this. So let's just quickly go through them with the analogy of the chariot. We already discussed the chariot, the king and the monk. So here's a chariot. So what is a chariot? It's a collection of parts. Typically it undergoes chariot motion. If you close your eyes, imagine a chariot moving, you imagine it moving in a certain way. The whole object moves, the wheels turn together. So it has some typical behavior. You all understand what a chariot does. So we have this notion of a chariot. So when is this a meaningful idea? So let's just ask a few questions. When is a chariot a meaningful idea? So here are some conditions. So first, it should have many parts. It should have all the required parts: wheels, spokes, axles, reins, yoke. They should all come together in a place. They should come together in the correct order. You should not have the wheel on the top. All of that should be present to call it a chariot. And each element should have the correct properties. The wheel, for instance, should be round. You cannot have a square wheel and call it a chariot. The wheel should rotate. You should be able to understand how the wheel will behave. We know how a wheel behaves. It should have the correct properties. And all the elements in the chariot interact with each other closely. So they influence each other very strongly. So one wheel cannot just roll away independently. If you push one wheel, the other wheel will also move. So they're constrained together. One pushes another and feels supposed to. So all the elements interact with one another. Together, all of this, in the language of physics, we'll call this complexity. So complexity, what we say is, there are many parts. We understand each part separately. We understand its behavior very well. For instance, here we understand what a wheel is. And we have all these parts that have come together, that interact with each other, that influence each other. That kind of a system is called a complex system. Anything with that character has complexity. So a chariot has a certain level of complexity. A chariot must have all of these elements. They should all interact in a certain way. It has a certain level of complexity. Only then you can define it. That's of course a chariot, but for any construct, any idea, any theorem, any law that we write, it always assumes a certain level of complexity. So please think about this. This is not at all a trivial state. Not so easy. So if I write Newton's laws, I try to describe a ball that is bouncing. I'm already assuming a certain level of complexity. I'm assuming that the ball is a certain size, there are many particles together, the ball's structural integrity is preserved, I throw it, it wants to shatter into pieces, it's not made of gas. All of those things are assumed in any status, any law. Electromagnetism, classical mechanics, statistical mechanics, anything you think of, assumes a certain level of complexity. That's something we usually don't think about. Okay, let's move. So here is another important notion that we should understand. That's the notion of a scale. Let's again go back to the chariot. Try to think of what it is. So a chariot it's a collection of parts. It typically undergoes this chariot motion, as we discussed. It has a characteristic way of moving. When is this meaningful? In what conditions can we think of it as a chariot? So here are some conditions. First of all, the speed should be low enough. If you try to move a chariot at 300 kilometers per hour, it will disintegrate. A chariot is only meaningful at a certain speed. Only some low speeds, terrestrial speeds that vary. It's only meaningful for weak disturbances. If I pull it by a horse, or if 4 people together push a chariot, the chariot will move in the correct fashion. If you take a hammer and a chisel and you hit the chariot, it will just splinter away. It won't move. So you should disturb it weakly. You should not disturb it strongly. You shouldn't shoot a bazooka gun at the chariot. Well, you can, but it will not have the properties of a chariot anymore. You should also only look at it for a reasonably short time period. You cannot park your chariot outside, come back after 200 years and then find the chariot. The chariot will just disintegrate. The chariot Pari gave to Mullah is probably gone. And it should also has a certain length scale associated with it. If you try to observe a chariot from outer space, you will not see anything. You will not be able to even describe it. So your resolution is too weak. Chariot moves over certain distances. Similarly, you should not see too closely. If you stand right next to the wheel, all you'll see is the wheel wobbling. You will not see the chariot move. So every time I have a construct, an idea like a chariot, I'm assuming a certain speed, a certain strength of disturbances, a certain time scale, a certain length scale. All of these together define a scale. And similarly in physics, everything that we talk about has a scale associated. Any concept, any notion that we have. We talk about a star has a certain scale, certain time and scale, certain lifetime. You can talk about a ball, you can talk about a table, you can talk about an atom, you can talk about an electron. They all have certain time scales, length scales, energy scales associated. Any law has this simplicity. So let's see some examples. Let's do this. Good. So here is an example of a simple physical law. Suppose I have a ball and I try to bounce the ball and I want to explain the motion of it. You all know I can use Newton's laws to explain how a ball moves. Or let's imagine I throw a ball. I can write initial velocity, find final position. So those are Newton's laws. They describe motion and they have a certain input. The input is mass, size, velocity, things like that. They go into Newton's laws. So we can also practice. So now suppose I glue two balls together. I stick them together. Glue. So two balls are attached to each other. Now I throw that pair, the balls that are stuck together, I throw them. Imagine I do that. And I want to describe their motion. I want to find out how far they will go. I again use the same laws. It's just Newton's law. The same law will work for this, except the mass is now twice the mass. It's the same laws explain a single ball. They also explain two balls. They also explain 10 balls or 100 balls. You stick many balls together, the same laws will apply, except the parameters change. Instead of mass, you put the bigger mass. So let's go to the next slide. So let's even think about this for a bit. So we talked about starting from a ball, you increase the number of balls, 2 balls, 10 balls, 5 balls. But let's even think of a single ball. What we call a ball is actually many objects together. If you think of a tennis ball, there's an outer layer, there's an inner layer, there's air inside. It's actually a compound object, it has many things together. So how do we describe such a ball so simply? How can I write one Newton's equation to describe something that has so many parts? It has 10 to the power 23 molecules inside. How can I do that? And that's a beautiful feature of physics. So the equations of motion that describe motion is separated into different sectors. They're reducible sometimes. You have equations for net motion, which is overall motion of the ball, rotation, something like this, the ball spins, or strain, or the ball is squished. Say. So if I'm interested in net motion, I need not worry about these things. Like I can only write one equation for net motion. And as long as I'm interested in net motion, overall motion of the ball, all I need to use is Newton's laws, and all the masses, every object there, the masses just add up. The equation for a collection of properties becomes one equation with the mass just adding. That's a very beautiful property of physics. So the same law, just Newton's law, applies, but just with a bigger mass. Okay? I hope you're all convinced. Please type if you like. Okay, so what we can say about this in a more philosophical tone is that the same laws describe the components as well as the whole. The same Newton's law applies to one ball, it can also apply to 100 balls. The same Newton's law applies to one layer of the ball, it also applies to the whole. In this kind of a situation, we'll say the scale has changed. You had one ball, suppose I go to 100 balls. The scale has changed. However, the same law applies with a quantitative difference, not a qualitative difference. The same law, it's just that the numbers that go in, the mass changes, the law remains the same. Qualitatively the same. This we are all familiar with in our day-to-day lives here. If you can, you know how to cook for one person. If you want to cook for 10 people, you just take 10 times the ingredients. Maybe take you 10 times not the time, but still the same. It's the same procedure, just scaled up. That we are all familiar with in many contexts. But let's look at another example, also well known in physics. Let's look at the next slide. So here is another paragraph. So here is J.J. Thomson's experiment. It is the original sketch. So 1897. So Thomson's discovery of the electron. So he has a metal plate somewhere labeled C over there. He has a metal plate, and what Thomson saw was particles are shooting out of the metal plate. And they're what we call electrons. So now we know that everything is made of electrons. Every object that we see, things we feel, all contain electrons. Let's just take a ball of metal. You had a ball of iron or copper. It contains lots of electrons, made of electrons. That we all know. However, so the statement you can make is electrons make the metal. The electrons are a constituent of the metal. However, the laws that electrons obey are very different from what the ball itself obeys. The whole metal ball obeys Newton's laws. I can bounce it, it has momentum, it has velocity, all of Newton's laws apply to it. But the electrons that make it do not obey Newton's laws. They obey the laws of quantum mechanics. So here is another picture. This is Davidson in Germany in 1927. They used an experiment with this, the double slit experiment. You may have seen it live. So they shot electrons through a filter which has two slits. And then if you imagine if you're just shooting electrons and there are just two slits, you might see like two strips at the end. You put a screen. But actually you see many strips. You see, this is the final result. It's like this. You see bands like this. So there are many electrons go here, many electrons go here, very few go in the middle. This is a characteristic property of waves. So the electrons actually behave like waves, they don't behave like particles. And that is part of their quantum nature. They have wave nature and particle nature. Whereas the ball we know has no wave nature. If I have a big metal ball, it's a particle. Behaves like a particle. Doesn't float away like a wave. Doesn't. So here is the situation. So electrons obey quantum mechanics. They form materials. They are the building blocks of materials. But say a metal ball, the metal ball obeys Newton's laws, which is a very different law. So there is a philosophical change here. There's a qualitative change. So the physical law changes qualitatively from one scale to another. You look at a single electron, the law is different. You look at a ball, a metal ball which contains 10 to the power 23 electrons, the law is different. You cannot use the same law to describe this. So we call this a qualitative change. The form of the law has changed. It's not just a number that's changed, the form of the law. So we can say that the physical law has changed qualitatively due to a change in scale as well as complexity. When you shoot single electrons, usually they are very high energy. But you take a metal ball, it's very low energy. So the energy scale is become lower. And of course, the metal contains 10 power 23 electrons. Complexity is increasing. Many electrons are bouncing off each other. Complexity is also increasing. So by changing scale and complexity, you've changed the nature of the physical. This is an example of emergence. We will talk about this a little bit more. Let's go to one. So here is this is not an example of emergence, but it's also a good thing to think about. So laws will change with scales. That is something natural to expect. So let me give you an example. If you have a particle that's moving due to some force, you know it's described by Einstein's special theory of relativity. That describes this. Especially if the object is moving at a very high speed comparable to the speed of light. Then it's described by Einstein's special theory of relativity. However, if that same object bounces off something and then comes off at a very slow velocity, moves very slowly, then it's well described by Newton's laws. Of course, historically, Newton's laws were discovered first. Einstein's special theory of relativity came later. So the same ball at low speeds is described by Newton's laws, at high speeds is described by Einstein's relativity. You might think the law has changed, but actually it's not true. It's not true because Einstein's relativity is always true. It explains slow balls as well as fast balls, fast particles, slow particles. However, when particles are moving slowly, Newton's laws are a very good approximation to Einstein's theory. In this sense, you might think the law has changed, but actually the same law. It's always Einstein's relativity. It just takes a more simpler approximate form in some ways. Okay. So this is not a qualitative change. This is a counterexample. So just please bear this in mind. There are different ways in explaining change. Good. Okay. Let's go to the next slide. Okay. So here, let's give a definition of emergence. This statement is very famous. You might hear it in many places. The whole is more than the sum of its parts. You put things together, the behavior you get is not just all the things together, but something more than the whole is more than the sum of its parts. It's the appearance of qualitatively new laws and constructs due to changes in both scale and number. So to change both the scale at which you're doing something, also the number of particles. Both scale. So let's just go through these quotes. The beautiful quotes by P.W. Anderson, the founder of modern condensed matter physics. Says the first quote is the behavior of large and complex aggregations of elementary particles is not to be understood in terms of a simple extrapolation of the properties of a few particles. Instead, at each level of complexity, entirely new properties appear, and understanding the new behaviors requires research, which is as fundamental in its nature as any. So you put things together, you get new laws, and you have to study. You just know, if you know what a single electron does, you cannot predict what a metal will do. So that's a new area, you have to study it, it's equally fundamental. Here is another beautiful example in its book. It says, You're so accustomed to the rigidity of solid bodies that it's hard to realize that such action at a distance is not built into the laws of nature. It's strictly a consequence of the fact that energy is minimized and symmetry is low. So essentially what he's referring to is the rigidity of solid bodies. So let's go to the podium again. If I push the podium from one corner, you all know it's a solid. This podium is very sturdy. Imagine a more wobbly podium. If I push it, that end will immediately move because it's a solid. I push this, it moves. It's rigid. But really, I only apply the force here, but the particles there move, objects there move. That looks like action at a distance. I'm acting somewhere here, and I see a consequence very far. Of course, it doesn't violate any relativity rules, but that is a consequence of rigidity. This has the property of solidness, where distances between entities are fixed. That's why you have this problem. And that itself is an emergent problem. It's because you have so many particles, they're all constrained, they're all touching each other. So if you push one end, the other end moves. So that's a very nice example that we should all keep in mind. A solid is an emergent phenomenon. There is no reason to. You might not guess that if you put many things together, it will become a rigid body which can preserve its shape. That's something not rigid. Okay, so that's big philosophical introduction. I'll give you some simple examples from our recent research in my group, so with my students and some collaborators, where we look at simple magnetic systems and we can illustrate how emergent properties come. How you can get new properties by just putting things together. Hopefully it will be clear. It's a very simple, it's just some 3 spins, 4 spins, you can get some new emergent properties. And so I'll try to explain those to you. Okay, so for this purpose, I'm going to consider some objects like this. So these are common motifs in many magnets. Many interesting magnets have these shapes as building blocks. They're built by putting many rods together, many triangles together, or many tetrahedra together. So this is a tetrahedron. It's shaped with 4 vertices and 4 faces. It's a regular tetrahedron, like a pyramid. These are very common faces. So we have magnets. So what that means is at every tip, at every vertex, so here for instance there are 4 vertices, every vertex we have a spin. And the spin for the purpose of this talk is just an arrow in 3 dimensions. It has a fixed length. So it is something like this. I brought some small tools to demonstrate this. So a spin is just something like this. It's an arrow. It has one end, it has a tip and a root. This is the root of the arrow, that's the tip. The spin is just something like this. It can point in any direction. The origin is fixed. It sits somewhere, it points. Let's just think of that. It's just a vector in 3D as a spin. That's enough for the purposes of this talk. Okay. So in this family of systems, you take a rod, a triangle, or a tetrahedron. They have a very nice property, which is as follows. You look at the energy, right? So at every point you have a spin. For instance, here you have 4 spins. You have 4 vectors. This vector can point in some direction, that can point in some direction, that can point in some other direction. There you have 3 spins. There you have 2 spins. In each case, if I ask what's the energy of the system, the energy is just the sum of the spins whole square. I'll illustrate what that means. It's a vector sum. For those of you who understand vector addition, you know what this is. You just take all the, so here for instance n is 4. Just take s1 plus s2 plus s3 plus s4, 4 vectors, add them and square. That's the energy. Here you add 3 spins and you square. That is a very simple property that allows us to explain it. Let's go to the next slide. Okay. So the energy is given by sum of the spins whole square. This is some number. The lowest value of the energy is 0. Imagine the sum is 0. That's when this energy is minimum. You add, after all, this is a positive quantity, something squared. The lowest value you can have is 0. When the vector sum of spins must vanish. Let's just do some nice geometrical exercises. How many ways can this be achieved in each case? We'll go through these cases, we'll see one. Let's go. Okay, so please feel free to stop me anytime if you like. So let's consider this example. So this is just the dimer, just 2 spins. Imagine you have 2 spins and you have the same condition. You have one spin there, one spin there, and the energy is the sum of the spins whole square. When will that be minimum? It will be minimum if the sum is 0. Yes, it is possible. I'll show you. So the sum of spins whole square is the energy. So here is a simple example. Take the first spin to point up, second spin to point down. S1 plus S2 is 0. Sorry? Yes.
So there can be other factors which is contributing to the energy, right?
There can be other factors. So in these systems, the spin is the only relevant variable. For instance, you might imagine that the triangle distorts or the tetrahedron does. Those things don't happen in these systems. I suppose that's what you're asking, right? So here, spins are the only relevant variables, and there exist real systems in this form. And okay, so I can minimize the energy. So for any of you here, if you're not familiar with vector addition, it's just something like this. I start with one spin. This is my initial point. I place the first spin in some direction like this. Then the second spin, I have to start from here, and then I have to point it in some direction. Now the total spin is simply, I start from the original point and go to the end point. Now if the total spin has to be 0, I have to have something like this. I go from here to there, and then I come back. Then I come back to the same point, then that is the lowest energy point. Okay. Now let's ask the question, how many ways can I do this? I could have placed the first spin in any direction. Right? I could have placed the first spin anywhere. The second spin will just go sit in the opposite direction. So I can place the first spin in whichever direction, it doesn't matter. The second spin always gets fixed. So how many ways are there? It's just it's equivalent to the number of points on a sphere. You can point the first spin in any direction on a sphere, the second spin is fixed. These are all the low energy states of this dynamo. Okay. So you can say that the low energy states are like the surface of a sphere. They represent where the first spin points, and that forms a two-dimensional space. The surface of a sphere is two-dimensional. So if you take any particular, if I say this is my low energy configuration, I can move it in two ways such that I still preserve this tension. I can move it like this or like that. There are 2 degrees of freedom. So we can ask, what is the low energy behavior of this kind of a system? So I'm just giving a qualitative picture here. You can also work with the mathematics with this. So the qualitative answer is this. So at low energies, you think this is 2 spins with some energy. It actually behaves like a particle moving on a sphere. You can see what is the reason for that? The reason is that all the low energy states of the 2 spins map to points on a sphere. I just fix the first spin and the second spin goes there. So the position of the first spin on the sphere that represents the state. How many states are there? There are as many as there are points on the sphere. So the low energy properties of a dimer actually look like a particle moving on the sphere. This we can show mathematically. So this is a very simple example of emergence. You have 2 spins. You put them together with a certain energy, or they couple to each other in a certain way, and the resulting object behaves like a particle on a sphere. So that is something different from what we started with. Just 2 spins, you get something. Okay. So let's do one more example. Let's perhaps skip this. Let's go to the next slide. Here is another example. So suppose I have 3 spins on a triangle. Now my condition again is I have to have 3 spins, and their sum has to be 0. I have to add the 3 spins to get 0. How can I do that? You can think about it a little bit. So let me just, before I demonstrate with these sticks, you can just look at this. So if I have 3 vectors and they should add to 0, all 3 vectors should be in the same plane. And one of them lies here, the other 2 should lie here. So this angle should be 120 degrees. This is 120 degrees, this is 120 degrees. That's the only way 3 vectors can happen. So let me just demonstrate with these sticks. Hopefully you'll see. So let's say first spin I place it this way, some arbitrary way. The second spin I should start from where the first spin ends, and it has to go somewhere there. Now I've just added 2 spins. The third spin I start from where this started, and it has to come back to the same point. Only then the energy is 0. Only then total is 0. The only way I can do it will always form an equilateral triangle. You cannot do something like this. If you do anything else, you will not get 3 spins added. Is clear? I'm just taking 3 needles, putting them end to end. If I say I start from here, I go there, and I come back to the same point, then I will form an equilateral triangle, whatever you do. There is no other way. So you can ask, in how many ways can I do this? So here is a demonstration. I can make an equilateral triangle like this, I can make an equilateral triangle this way, that way, anywhere. I can rotate this in front. So if you imagine this, if you think about this a little bit, you can convince yourself that all possible such low energy states are just equivalent to rotations. You start from one equilateral triangle and you rotate it somewhere. So that's already a very interesting property. So the low energy states of this are all just rotations. So how many do I have? It's the number of rotations that I can do in 3-dimensional space. So let's move to the next slide. That actually tells us a beautiful mathematical property. This system of 3 spins on a triangle, this energy, has these low energy properties. At low energies, it looks like a rotating sphere. Okay, what I'm saying can be said mathematically very precise terms. I'm just giving you a qualitative picture. So imagine I have a sphere. It has no special direction. It's just a uniform sphere. But its center is fixed, but it's allowed to rotate. And you ask, what are the energies of that object? If you look at the system of 3 spins, it will have the same energy. It will have the same properties. So the system of 3 spins, this kind of a constraint behaves like a rotating object. Why does it behave like a rotating object? Because it likes to preserve this condition of having equal zero spin. It's just like maybe a simpler example to think about it is the wheels of a chariot. Why don't the wheels of a chariot just break away? One wheel goes there, one wheel goes there. Because it costs a lot of energy to break a wheel off the axle. The wheels are stuck to the axle, it costs a lot of energy. Because of that constraint, because the energy is low, of course if you kick it very fast, it might break. But in usual circumstances, the wheels will move together and it will look like one chariot. The same way, the 3 spins together look like a rigid object, a rotating sphere. This is rotating. Okay, let's maybe have one more example and maybe finish up. Sure. Let's skip. Okay, let's maybe go back to this. So here is a nice geometric example. So this, maybe you can all imagine, and if you are, I'm sure, mathematically very talented. So imagine I have spins, but the spins are 2-dimensional spins. My spins are only allowed to be in the xy plane, in this plane. They're not allowed to come out like this. Now I have 3 spins, and their sum should go to 0. How can you do that? You must have 3 spins. Again, you must form an equilateral triangle. But the triangle must always lie in the plane. You're not allowed to rotate it like this. If you come out, then you break the condition. All spins must be in the plane. And the triangle can only be like this. And then you can rotate this within the plane. You can have all kinds of rotation. Actually, if you think about it a little closely, there is another set. There are 2 families. So imagine this condition. I put my first spin this way. Then the second spin I turn right. So this is of course 60 degrees. Equilateral triangle, so 60 degrees. I turn right, and then again I turn right. So 1, 2, 3. I take this object, and then I can rotate it in the plane. And they're all equal energies. Here is another example. I put the first spin here, but instead of turning right, I turn left. 1, 2, 3. So please convince yourself. Look at these 2 pictures. If I rotate that object, I can never get this. If I rotate it inside the plane. If I rotate it out of the plane, I take this, I flip it over like this, I will get this object. I flip it over, I'll get this, but I'm not allowed to flip out. I'm only supposed to stay in the plane. Then I can start with this, I can do any rotations. I can start with this, I can do any rotations, but they will not mix. It's separate, that's separate. So the moral of the story is, there's 3 spins with 2D spins. This behaves like a circle because I can rotate it in any way. Gives me like a 360-degree angle. Like that. This behaves like another circle. It's 2 disjointed circles, 2 separate circles. Let's go. So this system of 3 spins in 2D behaves like a particle that lives on 2 separate circles. The particle can be here or there, but inside each of this. This can be made more precise. Actually work it out. Actually, it's also a quantum particle. So we take only quantized energy levels. This we can show. Right? Let's go to the next slide. So here is, if any of you have seen quantum mechanics, this is the only data I'll show. There is some examples. So you take these 3 spins. The spins are actually quantum spins. That's a spin quantum number, S789, you can take any value. And you look at the energy spectrum of this. You see that there is the lowest energy state. There are actually 2 points. doubly dependent. Two possible low energy states. Then the first exact state is fourfold. There are 4 states, and there are 4 states. Okay? Don't worry about it much. Just the same as a particle that's living on 2 circles. If you have a particle that's living on 2 circles that obeys a lot of quantum mechanics, the energies will be the same. You look at the energies also, it's squares. So 0, 1, 4, 9, 16, 25, 36. They're all squares of natural numbers. Like 1 square, 2 square, 3 square, 4 square. And that's another property of a particle moving in a circle. That's a quantum particle moving in a circle. So let's go to the next slide. So here is maybe the final example. Let's stop with this. And this is truly illustrates emergence. So I was very excited about this. So let me tell you about this. So suppose we have a quadrumor, a tetrahedron, and 4 spins, 4 vertices, one at each corner. And these are 3D spins. Spins can point in any direction. Now I ask, the total spin should be 0. How many ways can I do that? So just please think about this for a minute while I take out the next new thing. Right, so I have 4 vectors, they should add to 0. Okay, so here is my demonstration. Let's see if it works. Maybe let's go to the next. Okay, so imagine I do something like this. Okay? So I start from here, then I go here, and I do this. You can tell I'm not very good at knitting. Better? So, this is correct. I'll get it right. So imagine
Need someone to look at it.
no, that's fine. This is interesting. This one makes me forces me to do it. So let's look at this. So this one, the bottom left, my bottom left. I started from my left hand, then I moved here, and the second spin begins from here, goes up. Third spin begins from here, goes there. Fourth spin brings it back to the origin, brings it back to the same point. So I have 4 spins, and they have added to be 0. Everybody can see this? Now, how many ways can I change this? Of course, I can rotate this over. I can do this, I can change this, that I can do. I can also change this angle. You see, you can change this angle. You can make it an acute angle like this. That you can also. But there's another thing I can do. So suppose I take this. I start from here. Suppose I can change the angle. I can also flip it like this. So there is another angle that I'm allowed to go out of the plane. So if you just a geometric property, play around with 4 vectors, asking how many ways they can act to 0. Turns out there are 2 angles you have to worry about. One is this angle. So this is exactly what I was trying to do. So first spin goes up, second spin, third spin, fourth spin. This angle, let's say, is some theta, one angle. And this angle can take any value. It can go from 0 all the way to 180. But apart from this, I have another angle. So this is the top view. So the top view, the vectors get distorted like this. And I have another angle that's allowed. So I have 2 angles, and then I can rotate this whole object in whichever way. Let's go to the next slide. So if we work out the effective theory, if you look at this object at low energy, very low energy, so I'm not allowed to break this condition. Total spin will always be 0. Ask what does it look like? It takes a very beautiful form. It looks like this. It looks like one rotating sphere and one 3-dimensional spin. This is some. Let me tell you what this is. The one rotating sphere actually came from the overall rotation. We discussed that if you have this, I can rotate it in any way. That part of it looks like a rotating object. It has the energy of a rotating object. In addition, there's another part that looks like a spin, just a new spin. But this spin, if you see, this actually came from this theta phi angle. So imagine if I have a vector in 3-dimensional space, if I have the length is known, I need 2 angles to describe it. Right? Some angle here, some angle there, that fixes this all. This is like, spherical coordinates, the polar azimuthal angles. Yes.
How it is coming here?
How it is coming?
Last previous slide.
Yes.
Driver in 2 dimensions.
Yes.
Driver in 2 dimensions as well as
So two different things are happening. So the trimer, the number of spins is different. There are only 3 spins. Quadrimer has 4 spins. It's a tetrahedron. Trimer is a triangle. That is different. The number of spins has increased. The space of spins is also increased. In the 2D spins, spin is only allowed to be in the plane. Now I have said the spin is allowed to be in anywhere, point in anything. Both things are changed.
When you're telling about the trimer, you spin also.
Yes.
Tell about the spatial orientation. In case of trimer,
Yes.
you tell about the equity in any direction.
Yes.
So, by this, whatever in 3D spin also, it can be in any direction.
That's true, but
At a particular instant, it could be in a plane only, right?
the quadrimer?
Yeah. At
Yes.
a particular instant, it could be like
It can
plane,
be,
right?
yes.
So, how we can tell that it is a 3D spin?
Yes, but that is not the only thing, right? So the trimer, it will always be in the plane for low energies. If it comes out, it cannot come out. The spins are constrained. Here the spins are allowed to go out. Sometimes they'll also be in the plane, but sometimes they'll be out of the plane. They both are. There's no contradiction. So here it's more general. So the quadrimer with 2D spins is also very interesting, but we won't talk about it.
Why did you say this is more emergent?
Yes. Who asked this? Oh yes, sure. Why is this more emergent? So for this reason. So I'm saying this 4 spins together looks like one rotating sphere and one 3D sphere. The rotating sphere just comes from the overall rotation you could have. So I discussed that you have this system of 4 objects, and you form some unit like this. This object you can rotate. You can rotate in any way. That part looks like a rotating sphere. That is something you expect. The whole thing has rotation symmetry. In the sense, if you look at it from, you tilt your head, it's still the same system, just as 4 spins. Right? The rotation symmetry is something you might expect, even before you started doing the drawing. But then, you had these 2 angles. These angles are some deflection angles, some deformation angles. This is an independent angle, that's an independent angle. They have nothing. But together, they come together and form a spin, a new spin. This spin was not there in what you started. You started with 4 spins, or each of them is a spin. And you only had 4 spins. Now we have some extra spin that comes out. It's not even a real spin. It's 2 angles that are deflections. Together they take the form of a spin. And this is the precise quantum mechanical statement. You can actually work this out. So this 3D spin is truly emergent. In the sense it's qualitatively new. It was not something you could have guessed before. You just put 4 spins together it looks like a new spin has popped into existence. So how did this come up? It just came up with complexity. So we put 4 spins together and scale. How did the scale come in? We said we're only looking at low energy properties of the 4 spins together. So I'm only looking at low energies. So it's not, the total of the 4 spins has to be 0. That's a low energy spin. So scale and complexity together can bring about new objects that you might not have guessed before. So maybe let's go to the next slide. Here's the summary. So we've spoken about emergence. So a good starting point to think about emergence is effective constructs. What is an effective construct? It turns out everything is an effective construct. We use them all the time. We don't stop to think about them. There are 2 aspects as far as physics is concerned: scale and complexity. They're both important. If you change both of them, the physical laws that we have cannot change. Quantum mechanics in a very microscopic scale looks like Newtonian mechanics at large scales. Even larger cosmological scales, it looks like general relativity. Things change a lot. So laws change with scale and with complexity. And in particular, you can have qualitatively different descriptions, laws, objects that appear at different scales, and that property is called emergence. So magnetism provides a very very beautiful playground. There are also real materials, the real molecules that have these shapes. I have not discussed them. It's a more detailed discussion. It provides real examples where even with very small objects, 3 spins, 4 spins, you can see beautiful emergence. You can understand how this kind of a property can emerge. And then you just scale it up and you can see something like a solid can emerge in our day-to-day existence that preserves its shape at low energies. So thank you very much.